Hi students, welcome to the new episode. In previous class we discussed Ohm's law, the factors affecting the resistance of the conductor and also known as laws of resistance, and some concepts of ohmic, non-ohmic conductors. Today we will discuss combination of resistors. The combination of resistors basically containing two parts. One is resistors in series combination and resistors in parallel combination. Resistors in series is used to measure the effective resistance of the combination of resistors when they are connected in series. For that, we will have to derive an expression. So, if you derive any expression, it consists of four folds. Number one, consideration. Number two, assumptions. Number three, manipulation. Number four, result. Consideration, I wrote here as a side heading, but don't write when you write in your books. It is just only to understand, to give the content very easily I gave you. So, I am writing here consideration, but don't write in your book. So, what is the meaning of consideration here? What you are taking in the circuit is called consideration. This generally starts with consider. Now, see this, what you have taken here, three resistors R1, R2 and R3 connected in series. That you write here, quite simple. See that, consider three resistors of resistances R1, R2 and R3 are connected in series. So, this is over. This is called assumption, consideration. Assumption. These assumptions start with let. Let V be the potential. Let I be the total current. Let R be the effective resistance. Then come to your manipulation part. According to Ohm's law, see the diagram. According to Ohm's law, what you can write, V is equal to IR, just I wrote here. Now, from the circuit, just I am manipulating, I can see that. I am doing some work. From the circuit, this V is divided as V1 plus, V2 plus, V3. I am writing this. And from 1 and 2, see that this is V and this is also V. I am equating these two. That I wrote as from 1 and 2. So, from 1 and 2, this IR is equal to V1 plus, V2 plus, V3. This is equation number 3. Students, see this V1. What is V1 basically when you see the diagram? It is the potential drop across resistor R1. Apply Ohm's law here. What is Ohm's law? V is equal to IR. Now here what is V here? It is V1, isn't it? And what is I here? I. What is R here? R1. Therefore, if you apply Ohm's law here, you will get V1 is equal to IR1. Come on students, if you apply here Ohm's law, what you will get? V2 is equal to IR2, isn't it? Now, similarly, can you apply Ohm's law across this resistor R3? Yes, we can apply. So, in this case, V3 is equal to IR3. Once again, first you considered. What did you consider? Three resistors you considered. How they are connected in series? Sir, no. That I am writing on the board. Consider three resistors of resistances R1, R2 and R3 are connected in series. Power. Next what? Assumptions. Assumption starts with let. Let V be the potential, let I be the total current, let R be the effective resistance. Assumptions part over. Now come to this Ohm's law. According to Ohm's law, you know that Ohm's law, V is equal to IR, that you write. So, V is equal to IR. Now, manipulation part. From the circuit, observe this V is divided into V1 plus, V2 plus, V3. Just I wrote here as equation number 2. from 1 and 2. This is equation number 1, that is equation number 2. Whereas V and V both are equal. So therefore, can I equate these two? Yes, I can equate. So IR is equal to V1 plus V2 plus V3, equation number 3. So far, so good. Now here, what is V1? What is V2? What is V3? What is V1 here? It is the potential drop across R1. Come on, say what is V2? Potential drop across R2. Then what is V3? Potential drop across R3. So V1 is equal to what? Apply Ohm's law here. If you apply Ohm's law exactly here, what you can see? V1, I and R1. So apply Ohm's law, then V1 is equal to I into R1. So I wrote here V1 is equal to I into R1. Now apply Ohm's law here, V2 is equal to I into R2. Apply Ohm's law even across this, V3 is equal to I into R3. Can I substitute V1, V2 and V3 in equation number 3? Yes, I am substituting. Once again what I said? Can I substitute V1, V2, V3 in equation number 3? Yes, I can substitute. I am substituting. So substitute V1, V2 and V3 values in equation number 3, and IR is equal to IR1, which is equal to V1, plus IR2, which is equal to V2, plus IR3, which is equal to V3. Now in this equation I am taking I as common. So I took I outside and whatever remaining I am writing. So I into, put brackets, R1 plus R2 plus R3. I gets cancelled. Then effective resistance R is equal to R1 plus R2 plus R3. Here, when resistors are connected in series, the effective resistance is always algebraic sum of all the resistances. I repeat, effective resistance in series combination is the algebraic sum of resistances. So the resistance value R is equal to R1 plus R2 plus so and so plus Rn. Therefore I can write this as the effective resistance R is equal to sigma I is equal to 1 to I is equal to n Ri. The meaning of this one is the effective resistance is algebraic sum of individual resistances. And here I will say two most important points in series combination of resistors. Number one, the effective resistance in series combination is more than highest resistance in the combination. I repeat once again, the effective resistance in series combination is always more than the highest resistance in the combination. Point number 2. In series combination, current remains constant, but potential divides. Once again, in series combination of resistors, current remains constant. It's always I, but potential divides, just like what we did. V is divided as V1 plus V2 plus V3. Did you understand this? Just I am going to parallel combination of resistors. Resistors in parallel. When you connect all the first terminals of resistors are connected at one point and end terminals are connected at another point such that potential remains constant and the current divides, then resistors are said to be connected in series. Now, as I said, it is fourfold consideration. So what we have taken, that we have to write first. So what I have taken, my dear students? We took 3 resistors. I am writing that. Consider 3 resistors of resistances R1, R2 and R3 are connected in parallel. This is our consideration. Once again, consider 3 resistors of resistances R1, R2 and R3 are connected in parallel. Next content is assumption. I told you that assumption starts with, yes, let V be the potential, let I be the total current, let R be the effective resistance. This comes under assumptions, my dear students. Now come to this, what you know in that circuit. According to Ohm's law, I is equal to V by R. You know that V is equal to IR, but here I is dividing, that's why I am writing I as major. So I is equal to V by R. I can name it as equation number 1. Now, from the circuit, I is equal to, come on, say that. What is I here? It is I1 plus I2 plus I3. Once again, equation number 1, equation number 2. What is here? I. What is here even? It is I. So, can I equate these two? Yes, I am equating. So, I am equating that in the name of from 1 and 2. From 1 and 2, V by R is equal to I1 plus I2 plus I3. Now, recall your magic triangle content. Here also you have to apply Ohm's law. Right. So, what is I1 here? According to your magic triangle, I1 is equal to V by R1. Yes or no? Similarly, I2 is equal to what? V by R2. Similarly, I3 is equal to V by R3. Now substitute I1, I2 and I3 in equation number 3. This is equation number 3. I am substituting. Therefore, V by R as it is equal to, in place of I1, V by R1 plus in place of I2, V by R2 plus in place of I3, V by 3. So, V by R is equal to V by R1 plus V by R2 plus V by R3. That implies V by R is equal to, I can take V as common. I am taking out V outside. So, V into 1 by R1 plus 1 by R2 plus 1 by R3. So, here this V gets cancelled. So, 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is our result. Once again, I will start here from this consideration. Just recapturation. Consider 3 resistors of resistances R1, R2 and R3 connected in parallel. Next assumption. This starts with let. Let V be the potential. Let I be the total current. Let R be the effective resistance. Don't confuse students. It is simply Ohm's law, only see that V is equal to IR, like V IR I am writing. Now, according to Ohm's law, as I is dividing, I am making it as major. I is equal to V by R. From magic triangle I took this. From the circuit, current is dividing, right? I is equal to I1 plus I2 plus I3. It's equation number 2. This is I, this is also I. I can equate these two. Even you also can equate that. So, from 1 and 2, after equating those two, I got V by R is equal to I1 plus I2 plus I3. It's equation number 3. Now, these I1 and I2, I3 are unknowns. You know very well, according to Ohm's law, I1 is equal to V by R1. I2 also V by R2. I3 V by R3. Now, I got I1, I2, I3 values. Can I substitute? Yeah, we can substitute. After substitution, I got V by R is equal to V by R1 plus V by R2 plus V by R3. That implies V by R is equal to, V is taken as common, 1 by R1 plus 1 by R2 plus 1 by R3. VV gets cancelled, then I got 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Students, are you feeling easy? Okay. Then, most important points regarding this parallel combination of resistors, I will say. So, the reciprocal of effective resistance of parallel combination is equal to the algebraic sum of reciprocal of individual resistance. I repeat, reciprocal of effective resistance of the parallel combination of resistors. Once again, the reciprocal of effective resistance of parallel combination of resistances is equal to algebraic sum of reciprocal of individual resistances. That means, if n number of resistors are connected in parallel, then 1 by R is equal to 1 by R1 plus 1 by R2 and so plus 1 by Rn. The most important points, the effective resistance in parallel combination is always less than the smallest resistance in the combination. I repeat, the effective resistance in parallel combination is always less than the smallest resistance in the combination. Point number 2. In parallel combination, potential, or simply you can say voltage, remains same. That means it will not change, but current divides. Once again, I will give you the clarity. In parallel combination of resistors, potential or voltage remains constant and current divides. Let us do problems based on series combination of resistors and parallel combination of resistors. I am giving you two problems. Let us solve. First, the problem is, if a resistor of resistance R ohms and length L is converted or bent into a circular ring like this, then the effective resistance between the two ends of diameter of the circular ring. This is generally the diameter. Even you can draw a line like this, a straight line. So, this is also diameter. Even if you draw like this, this also diameter. And if you draw this, this also diameter. Okay. Now, my major point is only one AB. So, I am finding this. Say, if this is divided like this, I can say this is entire length L. This entire length is divided into two parts, L by 2, L by 2. For L, the total distance is R. For L by 2, come on say, it's R by 2, isn't it? Resistance of the conductor is directly proportional to length, right? So, for L, it is R. For L by 2, R by 2. Say that this is first terminal, last terminal, last terminal. These two terminals are connected at one point. These two terminals are connected to another point. So, they are connected in parallel. Sir, no? Once again, see, these are the points, terminals connected to one point. These are the first terminals of the two resistors connected to one common point. So, according to parallel combination resistors, these two are connected in parallel. So, R1 is equal to R by 2, R2 is equal to R by 2. And we know the formula for parallel combination of resistors. 1 by R is equal to 1 by R1 plus 1 by R2. This is effective, let us say. And we can say this parallel combination means RP. So, in this case, I am substituting the values. It is 1 by R by 2 plus 1 by R by 2. We used earlier this as denominator of the denominator. This also denominator of the denominator. So denominator of the denominator will become numerator. Now I am writing like this. 1 by Rp is equal to 2 by R plus 2 by R. In this case, what is the LCM? R. So it is 2 plus 2. This is equal to 4 by R. That means Rp is equal to R by 4. Rp, that is effective resistance between the diameter, is equal to R by 4. You can do, my dear students, instead of R, if I use 40 ohms resistor, instead of R, if I use 40 ohm resistor, let us say that it is 40 ohms. What could be the effective resistance between the diameter of this particular content? You can simply say that in that case R is equal to 40, no? 40 divided by 4, it is 10 ohms. Okay? I am writing here, if R is equal to 40 ohms, if R is equal to 40 ohms, what is Rp? It is 40 by 4, it is 10 ohms. Another problem, second one, if R is equal to 28, come on, say, what could be your answer? Rp is equal to, come on, 28 by 4, it is 7 ohms. It is most important problem in all competitive examinations. Do you understand? Now let us go to problem number 2. In this case, first of all, they asked us to find what is effective resistance. To find effective resistance, first of all, you have to identify which are in series, which are in parallel. Clearly you can say that 15 and 30 are in parallel. So you write that mathematically. So R effective is equal to 10 plus parallel combination 15 is parallel with 30. So therefore this I can write as 10 plus 15 into 30 divided by 15 plus 40, because we know very well 1 by R1 is equal to, 1 by R is equal to 1 by R1 plus 1 by R2. So 1 by R is equal to, LCM is R1 onto R2, you will get R1 plus R2. Therefore, R is equal to R1 into R2 by R1 plus R2. Please use only for two resistors when they are connected in parallel. Use this formula when two resistors are connected in parallel. So effective resistance, it is equal to R1 into R2 by R1 plus R2. So I am using the same over here. Okay. So therefore this is equal to 10 plus 15 into 30 divided by 45. So it's 15 table, 15 ones, 15 threes, 3 ones, 3 tens. Answer is 10 plus 10, it is 20 ohms. We can find effective resistance between these two terminals. This is like this. First of all, how to write? First you write the formula, that is in mathematical formula, it is 10 series with this one plus parallel combination, 15 is parallel with 30. These two resistors are in parallel. Then I can write the formula R1 into R2 by R1 plus R2. I wrote here. Then 10 plus 15 into 30 by 15 plus 40. This part alone you do. 15 to 30 divided by 15 plus 40 is 45. Sorry, it is 30, 45. So, in this case, 10 plus 15 to 30 divided by 45, 15 table, 15 ones and 15 threes, 3 ones, 3 tens. So answer is 20 ohms. This is the effective resistance of this combination. Now, they asked us to find current through 15 ohm resistor. I will give you here shortest methods. I1 is equal to I into opposite resistance divided by total resistance. That is equal to, come on, so what is I value here? From the circuit, you can say that is 3 into opposite resistance 30 divided by total resistance 45. So it is 15 2s, 15 3s, 3 gets cancelled, 2 amperes. And similarly, I2 also you can find. I2 is equal to 3 into, what is opposite resistance to this one? 15. What is total resistance? 45. 15 1s, 15 3s, 3 gets cancelled, 1 ampere. Once again, to find currents in this branch and in this branch, we will go to one simplest method. That is, I1 is equal to I, that is total current, into opposite resistance divided by total resistance. That means, here I am writing 3 is the total current I into opposite resistance to 15 ohm resistor is 30 ohms divided by total of these two resistance or sum of these two resistances 45. So with the 15 table, 15 2s and 15 3s, and 3 gets cancelled, 2 amperes. Now apply the same rule here also. So current in that one is I2, that's equal to 3 total current into opposite resistance is 15 divided by 45. The 15 table, 15 3s and 3 gets cancelled, that's equal to 1 ampere. So like this, if you do the problems, you will get thoroughness in this chapter. So in next episode, we will discuss electric power, electric energy and domestic usage of electric energy and applications of energy, heat energy we will discuss. Until then, bye.